Today I'll talk about exact tensor completion via the sum of squares hierarchy, and this is joint work with David Stoyer. So, but before I talk about tensor completion, I'm going to, so in this talk, in the first part, I'll first describe matrix completion. Then describe the sum of squares hierarchy, conditions for exact matrix completion, and then how this generalizes to tensors. And then the second part of the talk, I'll describe how we show that these conditions are satisfied. So I'll start with the matrix completion problem, which is a very important and well-studied problem. So in the matrix completion problem, there's a matrix M. We're given some of the entries of M. And our goal is to complete M. So let's say we're given entries all over the place, and we want to complete M. So in general, this is clearly impossible.
Complete M. Expecting what?
Oh, I meant these to be arbitrary entries. Yes, but in the case that M has an additional structure, so if let's say if M is rank R, and the components are well behaved, so in this case, then we can solve it. So what I mean by well behaved is that what you don't want to have is a component that is sparse, has say only one in one row and 0 elsewhere.
You're going to define it formally or not?
I'll define it formally in the second part of the talk. But I will say the.
Informal, so you say.
Okay, that's fine.
So the component is the sum of rank 1 matrices, and they are not sparse.
Yeah. So here, I look at the singular value decomposition, UI VI transpose, and saying that all these are not sparse, because if one of them is sparse, then in order to complete this matrix, you'd have to sample all these entries, and here we'll look at what happens when we sample them randomly.
But I don't understand the problem. You start with a matrix, and then you say the goal is to complete the matrix.
There is a hidden matrix.
So it's a.
You know some things about this matrix. You know that it has small rank. You know that its entries are sort of.
You want to find what the matrix.
And you are given some subset, a random subset of the entries. What you want.
Yes, I was going to get to that. I think I'd say a canonical example is the Netflix problem. So in the Netflix problem, we're given the preferences of some people on some movies, and we want to complete the matrix. We want to predict like how well will a given person like a given movie that they haven't rated. And here, like it kind of makes it makes sense that it would be approximately low rank, because you can imagine that there's that roughly speaking, there's a few different kinds of people in terms of movie preferences, and a few different kinds of movies.
So is this a score or 0, 1?
Oh, these here would be a score. It does not have to be 0, 1.
In general, you're working over the real.
Yeah, in general, I'm working over the real numbers. So I should say, so in practice, the fastest way to like how it's solved in practice is you is you write it as an n by r times r by n matrix and optimize over these numbers.
Only with respect to the things that you see in the matrix, right? So
Yeah, with respect to the things that you see in the matrix. But here, I'm not going. But here, but in theory, the best theoretical guarantees that we have come from nuclear norm minimization, and that's what I'll talk about. That's what I'll talk about.
Also the optimization problem that you described is quadratic, so it's not clear how to solve it. What is in practice? What do you mean? What's the algorithm? I mean, that's the answer.
Well, it's a
It's an alternate minimization.
yeah. I think it's a non.
Optimize over the other and optimize.
But yeah, it is a non-convex optimization, so it's somewhat tricky to analyze theoretically. But there is a big line of work doing so.
But you want it to be approximate low rank, right? Not really low rank.
Yeah, I think that is also true in practice.
So you are going to define formally the problem, or you are not?
Oh, so the
The matrix complete. It doesn't matter. I just want to know because people are asking questions, and the question is whether you are going to define it formally or not, or this is just an intuition.
So here. Okay, yeah, I'll formally define the problem I'll be looking at. Yeah, it will be exact matrix completion. So M is a rank R matrix. So Mij, so M has a singular value decomposition. Sigma I ui vi transpose. And so we're given a sample omega of entries of M, where every entry is sampled with probability m over n squared. So m here is the expected number of samples. Yeah, and here we're assuming that there's no error in the measurement. So our goal is to complete M exactly.
So in this case, what it means is to find the decomposition into two matrices like that, whose product agrees with all entries in O.
Yep, and it is in fact the matrix M. Oh yeah, it's.
So why do you want to redefine the matrix M just any matrix of rank out of degrees. I mean,
Well, it's with high probability there'll be a unique matrix, a rank R matrix, which agrees.
Under some conditions that you were
Yeah, under assuming that you have enough samples, yes, and assuming you have enough samples and the components are not sparse.
The components are the UIs and the
Yes, and the components are the UIs and the VIs.
Does that decomposition exist if we're not in the real numbers?
The singular value decomposition, I believe the singular value decomposition always exists.
Yeah, over finite fields.
Let's see.
Even finite values, right? It's not even clear that
Yeah, if you
polynomial has solutions.
yeah, I guess if the field is not complete, so I guess I was thinking over the reals or the complex numbers, but yeah, if it's over a finite field, then I haven't really considered the problem over a finite field. Okay. Yes. So. Okay. So the method is that we're looking at is nuclear norm minimization. Minimization.
So before, one more question. So you define it formally. Now you're going to tell us what are the information theoretic conditions under which this is unique exactly, or you're not going to tell us?
I wasn't planning to, but I'd say that the information theoretic guarantees. Like they come from the coupon collector problem that you have to. Roughly speaking, that you need. I guess that you need R. That you need enough samples that.
Like constant times R times n if the components are not. You have several parameters: the sparsity, the
Yes.
length, this n, and how they're related for you.
Yeah. So the theorem is that. So I was going to say if we look at so what I'll talk about now is Benjamin Reck's paper, a simpler approach to matrix completion. Because our work, in some sense, is a generalization of this paper. And what he shows is that, if M, he shows that O of n are omega naught log n squared samples suffice. And I believe the information theoretic lower bound I believe it's nr omega naught log n.
And you're going to define this omega naught or mu naught?
Not omega naught mu naught. So I'll define it in the second part.
But that's a measure of sparsity.
But yeah, it's a measure of how well behaved the components UI and VI are.
The vectors look like random vectors, then mu naught would be a constant.
Yes, that is true. If UI and VI are random, mu naught is constant. Okay, so now let me define the nuclear norm, and I guess I've already written down the singular value decomposition, but let me give a picture for it. So singular value decomposition. M equals sum over I, omega I, ui vi transpose, and the picture here is that U1, UR, where R is the rank, sigma 1, sigma R, V1 dot VR, and it's very important that all the U's are orthonormal. And all of the V's are orthonormal. And then the nuclear norm which I'll denote by M, norm of M star, is just the sum of these singular values. Yeah, by changing the sign of U, yeah, that is an important note. By changing the sign of U or V, we can and will always take these to be non-negative. Okay, so now there's two questions. So the first question is, how do we minimize? So yeah, I should say, like, what this means. This means that we're solving the following optimization problem. We're minimizing over matrices X. And we're minimizing the nuclear norm of X over all X's which match our matrix on all of the sampled entries. So now there's two questions. So first question is,
There's a rank condition too, right?
nope, there's no rank condition on this.
The minimization of the
Oh,
sum,
this is-
you want many zeros there.
Yeah, there's no rank condition on here. So there's two questions. First, how do we do this? And second, why does this work? So so here I'm going to. So here I'll be looking at things through the sum of squares hierarchy. Yeah. So, and for this talk, I'll basically describe what the sum of squares hierarchy is doing here. So here we have a primal and a dual. The primal for the sum of squares hierarchy is what I call pseudo expectation values, which are a linear map.
The primal is the solution, what you are looking for, what you are finding.
Yeah, the primal is.
Variables are called pseudo expectation values.
So I'll get to like how this will be used, but yes, the primal will be like the optimization problem we'll solve, and I'll use the dual to show that it works.
No, all I'm saying is that usually when people see primal and dual in a book, then you're given the program, the constraints. Whereas in what you are showing us, it's actually the variables, not yet the constraints, right?
Yeah, I guess here I'm saying like a bit more generally what's going on, and then I'll say like the actual program that we'll be running. So in the primal we're optimizing over what are called pseudo expectation values, which are like a linear map from polynomials of degree at most d to r. The idea behind them is that they look like expected values over some distribution of solutions.
So just a second, we have m about n to the d variables.
Yes.
Because the linear map, we have to define it on the monomial. So we have this number of variables.
Yeah, it's a very large number of variables. So, and the conditions that we'll require are first that the pseudo one should be 1, and second that so all squares are always non-negative. So we better have that the pseudo expectation of any square is non-negative. And
Remind me why it's not an actual distribution. It has negative values. Is that?
so like it could have negative value. I guess if you try to extend it to higher degrees, then yes, it is possible that like, as some monomials at higher degrees would have negative values, but you don't see it by only going up to degree d.
Okay. Oh, I see.
You can think of it as if this is the low degree Fourier extension of some distribution. So maybe it's not easy.
Yeah, I guess it only looks like one as far as we can tell up to degree d.
A bunch of linear constraints on a space of 2 to the n variables. The solutions can be all non-negative or maybe not. Right? The moments of the distribution up to
Yeah,
some
the
degree are
moments.
just a bunch of constraints on vectors of length 2 to the n.
So essentially, you know what the first d or whatever d over 2 moments are, and then you don't have any information on it.
Yeah. All that.
Okay. Yeah, but as I was saying, like in terms of thinking about the second condition, it's useful to think about these pseudo expectation values in terms of the moment matrix. So the moment matrix is indexed by monomials of degree at most d over 2, and the entry in row p and column q is the pseudo expectation of p times q.
So all the columns are indexed by monomials.
Yeah. And then for any function, any polynomial g, like if we view g, so g is a linear combination of monomials, so we can view it as a vector over these monomials. And then the pseudo expectation of g squared is equal to like, g transpose times this m times g. And that means that this condition here is equivalent to this moment matrix M being positive semi-definite. Yeah, so that's the primal. So the dual is positive Stellan-Zotz proofs. And now here, all that they're saying is that if a polynomial g is a sum of squares, then it has to be non-negative. So now, if we have a polynomial that's a sum of squares, there's a one-to-one correspondence of an expression like this to a positive semi-definite matrix. And yeah, and here, if we want G in terms of this matrix Y, then to get the coefficient at monomial P, so that there'll be multiple entries of Y, which correspond to the same monomial, because you could have like x squared y squared is here, and xy times xy. They both correspond to x squared y squared. So as an example, like let's consider a univariate polynomial, x squared plus x plus 1 squared. So then the corresponding y would be the all ones matrix. So, but we could also re-express this polynomial like this, and which gives this Y matrix. Yes, so the idea here is that we can redistribute like a mass on entries corresponding to the same monomial arbitrarily.
So sometimes there are several ways of writing G as a sum of squares.
Yes.
It will reflect itself in this representation.
But could be there's also ways of writing G as a matrix such that the corresponding to the matrix is not positive semi-definite.
Yeah, and that we want to avoid. Like we always want this matrix to be positive semi-definite. Yes. Now all we'll use from this is that this, like, if G is a sum of squares, then its pseudo expectation is non-negative. And how this appears is that if we take the entry Y as dot product of M and Y, then this is non-negative. Okay, so now that.
And you say all this reduces this like the easy direction of the duality.
Oh yeah, this is the easy direction of duality. That's correct. So now I'll say what the actual program we're running is.
You probably want to say that this can be solved in n to the d time. This kind of program can be solved by semi-definite program.
Yes. I'm gonna keep this up, but. Yes, so yeah, it can be run in n to the O of d time. Yes. Okay, so now in order to minimize the nuclear norm, here's the program that will run. So we'll have variables x1 through xn, y1 through yn. So our objective function. So we're going to minimize the pseudo expectation of sum over a xa squared plus sum over b yb squared. And this is subject to the pseudo expectation of xa times yb is equal to mab if a and b are in omega in the sampled entries. So let me draw a picture for this. So if we draw the moment matrix, it looks like this, and we're minimizing the trace.
Same as on the left.
Yeah, it's the so.
Why is this the moment matrix? So can you say what the rows and the columns are? The labels are?
Oh yeah, the rows are
D is 2 here, right? The degree.
yeah, the degree is 2,
So this will be just,
and yeah, so the rows and columns are indexed by the monomials of degree in most 1. And here so this part is the xa's, and here's the yb's, xa's, yb's, and here we don't know what these are, but it turns out that this accomplishes this nuclear norm minimization.
And the A and B are diagonal?
These are not diagonal, and that's that's important. But yeah, I'll now describe the dual, which will explain why this works.
Yeah, so I don't understand what A and X and B are.
What is
Oh,
the
it's
variable
a
element in the problem? You said the variables are gave the potential names. What do they represent in the original problem?
so yeah. Okay, so the variables don't by themselves don't represent anything in the original problem, but what we'll have is that the pseudo expectation of xa times yb when we run this program is going to correspond to to mab.
Let's say differently. Let's say the matrix is of rank n, rank r, as you wanted in everything. What would the values then be? Like, what's the intended solution there?
Oh, okay. Thanks for reminding me. Yeah, but before I went to the dual, I should have said. So I should have said what the intended solution to this is. So the intended solution is so one feasible solution is this basically the singular value decomposition. Where in an individual term, the x's are going to be the coordinates of ui. The y's are going to be the coordinates of vi. And then what this will give is that we'll have
Xi corresponds to the ith row or something like that in U prime.
XA corresponds to the 8th entry of UI.
What do you mean entry? But
Because
it is a metric.
so here these are vectors.
Okay.
So
And then it takes the uniform distribution of those vectors or something.
And you weighted by the sigma I.
yeah, it's weighted by the sigma i's, but we'll have like x. So xi will be like the square root of sigma I. Yeah, I guess in the in one part of the distribution, it'll be the sorry. The idea is that XA is going to be the 8th coordinate of UI. YB will be the bth coordinate of VI. And if you yes, I ranges from 1 to R. Exactly. So this is essentially the singular value decomposition. And if you look at its trace, so
XA is sum of the value? When you say
it's not quite a sum. It's a distribution over these, each with it's a distribution over these vectors with different weights, and then.
So the thing you're minimizing is actually vector times matrix times vector, right? Right, that with that matrix, right?
With this here.
That's what I thought the expectation was. The pseudo expectation.
So here so here the pseudo expectation is going to be like an expectation over an actual distribution.
In this solution.
And the distribution corresponds to the solution given by the singular value decomposition. Let's see.
Does this correspond to this, the minimization of this norm that you said before? Because you said, right?
Yes. So it turns out that this program minimizes the nuclear norm. And so the first thing I'm showing is that this is a feasible solution. So its objective value is the nuclear norm, because if we look at a single if we look at the trace of UI transpose, that is just just the norm of UI squared, which is 1. I rather like the yeah, it's 2. Yeah, it's 2 times the nuclear norm.
So one question is, where do you enforce orthogonality, something like that, or is it something right for the picture?
So
You wanted the
okay, so here so it's a theorem that for any matrix, the singular value decomposition exists. So if we actually ran this program, we don't know what the singular value decomposition is. However, if we're here we're not running the program, we're arguing about it theoretically. So we're allowed to say So we're allowed to use the singular value decomposition in our arguments.
So it's not like you're looking for U and you're looking for V. You're looking for some matrix, and that will implicitly define some U and some V.
So so I guess here what I'm saying is that in the actual matrix M we have this U and V, and there's a corresponding solution to the primal. So that there's a feasible solution which gives this optimal value, and what I'm going to say next is that this value is in fact optimal.
But the program, this
Doesn't
square
explicitly
program
talk
does
about
not necessarily just give you values to all the
Just gives you a
monomials of degree 1 and 2
Yeah.
in this variable. That's what it will give you. It does not have to come from this distribution.
Yes. Okay.
Sorry, just again, basic question.
Sure.
Distribution is over polynomials, right? Or this pseudo distribution or
So
is it? I mean, it says
Pseudo
there is
distribution is just a bunch
function
of
from-
numbers. It assigns to every monomial up to some degree a real
okay,
number.
and this minimization problem is over this distribution.
over these two distributions. So I guess the
distribution, but not the value of the variable.
Right.
Right, I'm understanding. Sorry. The expectation is that, okay, I'm canceling the question. Understand.
no problem. Yes.
So, once you figure out what the x sub a's and the x sub b's are, what you're going to do, right? Solving your problem is sort of giving it a weight or coming up with values for them. Then the answer, the matrix that you ultimately want, the completed matrix, is on that board up there, is going to be simply the expectation of all of the degree 2 monomials that you can build from the degree 1 guys that you solve for. I mean, is the
Yes,
answer
the-
you're ultimately looking for e twiddle of xa, xb?
Yeah. That's right.
That's the completed matrix, right? Except not with a's and b's, with all i's and j's.
Oh, I sorry for the confusion. I was using A and B like as I and J, like as where I would usually use I and J. The reason is because I've labeled the vectors U.
Sampled ones are using the a's and the b's, but you're ultimately going to use those monomials for all the guys. And
It's going to output x. You will get
yeah,
that will be the matrix.
Yeah. The output will be X,
and that's the answer.
and that's the answer.
Thing you're looking for.
Yep. That's the answer.
And when you say that this is a feasible solution, so what do you mean? What is the pseudo distribution?
The real distribution over the singular vectors of this matrix gives an actual distribution which is feasible for the pseudo distribution relaxation. So if you have an actual distribution that's feasible as a pseudo distribution. And Aaron's saying that
Okay, so what is the actual distribution over the
So the actual
of the monomials of the form?
so the actual distribution is that the x is a vector with x sub I being the ith entry of the vector u times sigma I, and then the y's are the singular vectors v. So it's like a joint distribution over x and y. X takes value ui, and v takes value yeah, and then
For people who didn't see this is a relaxation. It's a program. It's a complex program, semi-definite program for computing something. The distribution that actually comes from the scalar value decomposition gives one feasible solution to it. But it may not be the minimum. This program may generate something, that doesn't come from a distribution, has much lower value. So you have to rule it out.
Okay, so
Okay.
it's more basic like that.
Mm. Okay. Yeah. So I'll now show that this. I'll now show that this solution is optimal. So Okay, so here's the dual that I'm going to be looking at. So first let's pretend that we actually have all the entries of M. So the dual is going to, so in that case, we can use the following dual. So we have the identity here. Here we'll take minus uv transpose. So not M, but minus uv transpose, and minus vu transpose here, and the identity. So so this is positive semi-definite because these have norm 1. And if we take the entry-wise dot product of our moment matrix with this,
Can you explain again why this positive semi-definite?
so
For the same reason that the 2x2 matrix which has 1s on the diagonal and symmetric and has a negative value that's less or equal to 1, and the off-diagonal entry is positive.
The diagonal
The diagonal is 1.
is big enough so it
Yeah,
equals
yeah,
all
big.
the
yes, the
If your eigenvalues on the diagonal are 1, the off-diagonal are at most 1.
yes, that's the idea. So if we take the entry-wise dot product of our moment matrix with the with this matrix here, then so the identity parts are going to give us exactly our, so yeah, so I'll call this y, call this m. So the entry-wise dot product. Oh, yes. Guess I'll call it Q then. So the identities part are going to give us exactly, it's going to give us exactly the objective value. And now the dot product. Now if we're given all the entries of here, so this is M, then we're looking at the entry-wise dot product of u sigma v transpose with minus uv transpose, and I claim that what will happen here is actually it'll be 2 times this from this and its transpose, and this will be precisely minus 2 times the nuclear norm.
Sigma is the diagonal matrix.
Oh yeah, I should have written that down here. Sigma is the diagonal matrix.
So the dot product is like XY transpose, right? So then the V transpose V cancels and the U transpose U cancels, and that's how you write it. Minus 2 sigma, is that?
I think it's not sure it's quite the transpose because it's.
The dot product is trace of the product of the matrix with the transpose.
Yeah.
Yeah, that's. Yes. That's correct. And so this is precisely minus 2 times the nuclear norm. And this has to be at least 0. So, and therefore this says that our objective function is at least twice the nuclear norm. So this solution here is optimal. Yeah, so it takes a little bit more work to show that it's unique, which I won't go into.
So can you, it's a little bit hard one question. So I understand the original Q.
Yeah.
And so what is it twice? So you build something, some proof?
Yep. I kind of I can choose y arbitrarily as long as it's positive semi-definite. So I think that's what I was going to get to next. What made this y work, and how yes.
This y was completely up to you, and you just because it was positive semi-definite, you know that the inner product with Q will be non-negative.
Yes.
And then you look at sort of you see sort of what's the polynomial that y corresponds to, and then so you write it down, and then you get some inequality for the expectation of for the objective function.
Yeah. So. And in this way, like this gives us the bound on the objective function. Yeah. So actually, one note before I described why this y worked and how we generalize if we don't have all the entries here. Like this argument shows that like once we fix these, and if we only vary over a and b, then the minimum is going to be the nuclear norm of X. So this semi-definite program does minimize the nuclear norm. Okay, so why did this y work?
So you are not going to explain why it works for partial.
I'm going to. I will explain that. But yeah, first I'm saying like what made this choice of y good. So okay, well, first thing is that we needed it to be positive semi-definite. The second thing is that when we took the entry y's dot product of q and y, so we got the objective function plus known terms. Again, it didn't depend on any choices that we could have made in the primal. And the third thing is that the actual the thing is that the components of the actual solution are zero eigenvectors of eigenvectors of y with eigenvalue 0. And what this means is that, and that's what makes this. So here we have this inequality. It's this condition that made the inequality tight, and gave us a tight bound.
So Q corresponds to the expectation,
yep.
And Y corresponds to a polynomial, and you take the
Yeah, a sum of squares polynomial.
And y depends on the metrics that you started with, right?
Yeah, we choose y.
Why? So when you say components, you mean a vector, a 2n length vector of the vi and ui?
Yes. So if we yeah, I should draw that. So
Just the equation that y is multiplied with the vector ui.
yeah, so
Zero. Yeah, that's what I'm checking.
yeah, that is the case. That we have id minus uv uv transpose minus vu transpose id. If we multiply this by the vector ui vi, then you can check that this gives 0.
It's like the complementary slackness conditions for this.
Yes.
For duality. It's not completely obvious to me, but I guess it's easy to see.
Well,
Oh, I see, sure. Because there is orthogonality. Yeah, so you use orthogonality.
yeah, I use the fact that the ui's and vi's are orthonormal, and that's what. Yes, that's what gives me this. Okay. All right. So now I'll describe what we do if there's so I'll now describe what happens if we don't have the if we don't know all the entries. So what if we only have some entries? So we can still give a.
Why would you only have some entries?
That's the whole problem, completion.
Yeah, so you're only given some entries of the matrix, and you want to complete it.
So far I solved the completion problem where the matrix is complete.
Oh, okay. Maybe that's why I was confused before. Okay.
Yes. So if we only have some entries, here are some sufficient conditions to get a proof as before.
Where did you use the fact that you have only two
They
Where
use
did you use
But
this
you
condition?
used it because you could say that the off-diagonal entry of q was equal to n. Was equal to n.
yeah. So I use it in taking the so because if I didn't, so I use it to say that this was exactly m, which allowed me to take the dot product with y. If I didn't know some of these entries, then q could have arbitrary values there, which throws off my dot product. But that's what I'm going to get to now. So here.
Sufficient conditions for optimality.
Yeah, for optimality. So the first condition is we want this to be positive semi-definite. So we want this matrix T to have norm at most 1. the second condition, which ensures that we know what the dot product is with Q, is that T A B equals 0 unless A and B were sampled. And the third condition so we again want to have that y times like an actual component of the solution is 0. And that implies that T times Vi equals Ui, and T transpose times Ui equals Vi. And so if you can find a T which satisfies these three conditions, then that gives a proof of optimality. So in the second part of the talk, I'll describe how you can find such a T. I'll finish up the first part of the talk by saying how this generalizes to tensor completion. The nuclear norm of M, yes, it says that the actual solution from the singular value decomposition is always feasible,
Okay.
and this and like if this y exists, that proves that it's optimal.
And then if you complete the matrix with those
So
solutions, then it means that it's the same.
So okay. So it takes a bit more work to show, like, not only is it optimal, but it's the unique optimal solution.
Okay.
But you can do it. But and once you do, then yes, it solves the matrix completion problem.
So this is where you use the fact that M is random, or you said something that that M is given in this form. It's not given. It has this form when U and V are I mean, you want to know that if you have the same nuclear norm, then it's unique and it gives you the same.
I think in the matrix case, you don't need in the case of matrix as opposed to tensor, what the information do you need on the you mentioned this new zero. Some of the existence of this T will depend on the
Yes.
conditions.
Whether or not this T exists depends on how many samples you have. But this is a set of conditions which says that if you can find a T satisfying these conditions, then the actual solution is optimal.
So you know that if you have a solution that has the same nuclear norm as M, then this solution is the same as M because it's unique,
So I did not show that part. So like that takes a bit more work, but you can also show that the actual solution is unique as well.
The only condition is that you wanted this Y matrix, the kernel should only be the UI, the span of the UI. I think that's essentially the condition.
Yeah, that is yes, the idea for uniqueness is that the null space of Y the kernel of y is equal to the span of the UI of the UI concatenated with vi, and what that means is that any optimal solution is going to be shoot, where should I guess I'll erase this. So any optimal solution has to be in the span of UI vi transpose. And then what you do is you'd say the only matrix in this span which matches M on the observed values is M itself. And that's how you'd show that the solution is not only optimal but in fact unique. Okay, so now I'll talk about how this generalizes to. Actually, I have a feeling it's a pretty good time for a break.
Okay, very good. 5 minutes, that will probably take longer.
Okay, so I'll now finish up the first part by describing how this can be generalized to tensor completion. So
Just one question, Aaron.
sure.
In the formulation for the conditions over there for T, if you wanted to just forget about the minimization problem, just formulate the dual, the maximization, you formulate a maximization problem with these conditions, this will be another program to compute the nuclear norm. Just the maximum of this without the maximum of the
wait, I don't think it would compute the nuclear norm, because actually this certificate here. That's something I should have said before. This certificate, this y, is independent of the singular values. It only depends on what the u's and v's are.
Yeah.
So that actually shows that this same y works regardless of the singular values. Okay, yeah. So now talk about the order 3 tensor completion problem. So it's a similar setup. There's a tensor T, which is the sum of R rank 1 components. And we're asked to recover T given only some of its entries. So information theoretically, this requires at least nr log n entries. So the other paper which inspired this work, by Boaz Barak and Ankur Moitra, a noisy tensor completion by the sum of squares hierarchy. Yeah, so they show that degree 6 s a sum of squares gives approximate use approximate tensor completion with, so here I'm going to hide some constant, some mu constant depending on how well behaved the components are. So let's see, I think it's r times n to the 3 halves. I think maybe like, I forget the power of the log power that they get.
Is that for random samples with hypo?
Yeah. Yes, with random samples with high probability.
No, so they assume this regularity, that's non-sparsity, or they...
Yeah, they also assume that this regularity, but I'm sweeping that under the rug. The however, at least as far as their argument goes, there is always some error. So the question we were asking is, is this error really necessary? And what we show is that so we give analogous conditions we give analogous conditions for degree 4 sum of squares to give exact completion. And we haven't yet been able to do it for general tensors, but we show that these conditions are satisfied. If the vectors are orthogonal, and we have O of r n to the 3 halves, mu to the 3 halves, where like this is related to how sparse the vectors are, log n squared samples.
Their algorithm works for r bigger than n?
Yeah, so their algorithm works for r bigger than n. And I guess that's future research to extend our techniques to the non-orthogonal case, but that's where we're starting. So okay, so let's try and generalize this to the.
Sorry, when you say expression of this?
Moments up to 4. I mean,
Yes.
so the matrix will be like n squared by n squared.
I see. Okay.
Yes. So all right, so let's try and mimic what we did for matrix completion. So here there's a bit of asymmetry, but it turns out that that's actually fine. So now we'll have variables a, y, b, z, c, and we'll minimize the pseudo expectation of sum over a xa squared plus sum over b and c yb squared zc squared. Subject to the pseudo expectation of xa, yb, zc is equal to tabc if a, b, and c were sampled. Okay, so the picture for that so here like xa, ybzc, xa, ybzc. So here we will have some x and x transpose, and yeah, here we don't really know. And then, so here, so let's make a first attempt at the dual. It won't work, but if we could do this, then it would.
So, by the way, I have some question.
Yeah.
Why don't you, also in this previous case, why don't you demand that on the diagonal matrix are diagonal? Because you are looking for orthogonal solutions. So you could demand it in the final.
That these are diagonal?
Yeah.
Because actually that's not the case for the actual solution.
Okay, but in the previous one, or at least
It's also not the case for the previous one. We'd actually get in this diagonal would be the sum over I of sigma I ui transpose. And if you just consider like one component, then this is like it's not diagonal at all. The thing is that its trace is the nuclear norm. Yeah, in the primal, these are not diagonal. I guess any other questions before I continue? All right, so here is a first attempt at the dual. Let's try and do exactly the same thing that we did for the trying to do exactly the same thing that we did for the tensor completion. Shoot, I guess I'll call this Z. No, I don't want to call that Z. Darn it. What should I?
T is now the original tensor. So
Yes.
I think you call the original tensor M. It's just it will be most consistent with everything.
Sure, I'll do that. Yeah, that's minus T transpose. So here, so if following the same logic as before, so the following conditions would be sufficient. So all right, so the first condition is that T A, B, C equals 0 unless A, B, and C were sampled. And we need that to know what so that we know what the dot product of Q and Y will be. The second condition is that the norm of T is at most 1, so that this is positive semi-definite. And the third condition, if we did this, it would be that that T times VI tensor WI equals UI, and T transpose times UI equals VI tensor WI. Okay, so if we could do this, then it would work. However, we can't.
You would need much more samples.
Exactly. I was going to say, like here we're effectively treating it as an n by n squared matrix, and it turns out that that the bound depends on the number on the length of the longer dimension. Yeah, it would require like R and squared samples, which is a lot higher than we want.
We multiply two dimension to 1.5 and 1.5.
Yeah, that would be amazing, but that's kind of hard. That's kind of.
And we're trying to do the next best thing.
Yes.
So, but do we see that again the original distribution on the? Is it obvious that the original distribution is a feasible solution, giving the sum of sigma is as objective value? Is it? I don't want to show us. I'm just asking. Because it's sort of asymmetric, and so maybe you can just say. So if we pick what will be the feasible solution? You pick the UIs and the other vector was really.
So it's
Square root. Okay, good.
yeah, it's the same thing is going to happen here. The
Previously, we didn't have M didn't have to be a symmetric matrix. Like it didn't have to be a square matrix.
oh yeah, it didn't have to be it did not have to be square. I just made it square to simplify to not worry about that. But yeah, it works just as well if it's not square.
And that's what this is, right? This is like treating it as a.
Well, as we're doing right now, but it's failing because it requires too many samples. So okay, so yeah, so that's failing. Any ideas for what can be done?
And just split it into 1.5 and 1.5.
Yeah, yeah. Unfortunately, it's not clear how to do that. Though, like, yeah, if you could do that, that would be amazing.
So you are keeping the primal as it is.
I'm keeping the primal as it is, yes.
So what you have is just too many demands on T, right?
Yeah, I have too many demands on T.
That's you want fewer demands.
I want demands that are easier to satisfy. Oh, I should say, like, this demand in particular is too strong because it would require that, I guess, for all B and C, that it requires that T has an entry for every B and C. So for all B and C, there exists an A such that T A B C is not equal to 0. But that requires n squared samples.
So what happens if you just demand that it's a rank 1, although that's not the T transpose times UI?
Yeah, this condition here is way too strong. Okay, so what we can do, there are degrees of freedom which we're not using. There's a reason why I kept this up here the whole time. So in the dual certificate, we're allowed to, we can have the same polynomial, and we're allowed to adjust y by shifting around mass among coordinates that correspond to the same polynomial. So, like, if here, let's say we have like y, let's say we had yb1 zc1, yb1 zc2, yb2 zc1, yb2 zc2, like these rows, and look at the same columns. Oops. yb1 zc2, oops, I'm running out of space, b2 zc1, yb2 zc2. So these I claim that these four entries all correspond to the same monomial, which is yb1, yb2, zc1, zc2.
So you just ask that their sum is 0, not necessarily that they are all 0.
Yeah, that's the idea. Like, we can shift mass around by, like, say, adding 1 to these and subtracting 1 from those. So that gives us a ton of additional freedom in this part. It does not have to be the identity. So with that in mind, let's try again.
But you still need to keep the PSD.
But I still have to keep it PSD.
PSD is implied by T is the smallest one. That's enough.
Well, I hear. Well, actually, this condition is also too strong. This condition is too strong. But what I'm going to say is that we have a ton of freedom here, and we're going to use it. So. Okay, so here's what our dual certificate will actually look like. Minus T transpose, and I guess I'll call this A. And it's going to be convenient to write A as the identity plus T T transpose T minus some R. And then I'll be looking at sufficient conditions for R. Okay, so so first we want that this to be 0. So we still have the condition that T vi tensor wi equals ui. And now if we look here, T transpose T times vi tensor wi. So T transpose T times ui vi tensor wi. From the above, this is equal to T transpose times ui. So what we need is that the identity and R cancel on this part. So we need that R times vi tensor wi equals vi tensor wi. The third, all right. So additionally, we need this to be PSD. So here if we use the Schur complement, then we need A to PSD dominate T transpose T. Just the identity, but like in general, if in the Schur complement, you take the inverse of whatever this is.
Yeah, but you don't need it.
But yeah, here I don't need it. So in particular, that means that the identity, we need the identity to PSD dominate R. And yeah, and in fact, we can show that the norm of R is going to be at most 1.
That's what you want.
Yeah. And then another condition is that we want this to equal the identity as a polynomial. So basically, it's the identity plus the shifts in mass. So we need that R is equivalent to T transpose T as a polynomial. And the final thing is, as before, we need that T A B C equals 0 unless A, B, and C were sampled. Yeah, so these conditions are sufficient for exact tensor completion.
They are sufficient despite the fact that you gave up on this reverse, this too strong thing.
Yeah.
So what happens in the matrix completion if you gave it up?
So in the matrix completion case, because we're only looking at degree 2 polynomials, we don't have this kind of freedom at all. It really does have to be identity.
I see, but you could do it in the matrix, same thing, but do the degree 4. Yeah, I don't know why.
The third constraint just came because we wanted the U has and V has to be in the kernel of the matrix.
Yes.
And the just check this with the corresponding constraint on the right. I guess that's somehow saying something about how the matrix acts on VI tensor.
Joe, I thought the two-form condition was that to transpose times UI is. That was, I mean.
Yes. Okay.
So what replaces this?
So because this is no longer the identity, it's it's this here that it's this condition on R that replaces it. Yeah, now R is an n squared by n squared matrix where we have a lot of freedom to choose, so we can hope to satisfy it.
So is 4 really where you're using the sum of squares to say non-trivial things about how you can change the semi-definite program without actually changing the solution?
Well, it's not the semi-definite program we're changing. It's this dual certificate. Exactly. This is the part where we're really using sum of squares, that we have this freedom in the dual certificate. Okay, so that concludes the first part of my talk. In the remaining time, I think I'll start by going back to the matrix completion case and talking about how we can find this T. Okay, and now that I've now that I've finally described where we're using the extra power from sum of squares, I'll erase this. So finding T. So, all right, let's recall the conditions for matrix completion. ID minus T transpose ID. So we needed that T AB equals 0 unless A and B are in omega. T VI equals UI, and T transpose of UI equals VI.
The norm of T.
Yes, and the norm of T is at most 1. So actually, before I continue, let me re-express this condition here. So I'm going to define PU to be the projector onto the subspace spanned by the UIs. And similarly, so PU would equal UU transpose. Where U is this matrix here. PV, similarly, PV will be the projector onto the VIs. And now I'm going to define a projection sorry for overloading T. I'm going to define the projection operator PT on a matrix to be PU of M plus MPV minus PU M PV. Okay, so what's going on here? So PT projects onto the following types of matrices. You can have UI and anything here. And the reason is if you apply PT to this, so PU acting on the left keeps it the same. So these two cancel, and you get your matrix back. And in following similar logic, you can have an arbitrary vector here and VI, because then when PV acts on the right, it preserves it. So then these two cancel, and you get your matrix back. But this predictor operator PT, it zeroes out everything orthogonal to like all of the UIs. And VJs. So for example, if you had like something here which is orthogonal to all UI, and orthogonal to all VJ, then PT zeroes out all of these kinds of matrices, yes. Okay, so now so now I claim that condition 2 is equivalent to saying that PT of T, sorry for overloading, T is equal to M. Yes, because these conditions precisely capture which elements here you have, and this is true for M. Okay, so with that in mind, I'll describe how we can find this T. So our starting point is going to be M. Sorry, not M, is going to be UV transpose.
Without the singular value.
That's the mistake I just made. But actually for simplicity, let's assume that is actually M. Like all the singular values of M were 1.
This is true here also when you have PT is equal to M. Is this only in the...
Oh, sorry. Yeah, I thank you. Yes, I made that. Yes, is equal to UV transpose. And for simplicity, let's say all the singular values are 1, so M equals UB transpose. Okay, so in that case, M satisfies. So M satisfies conditions 2 and 3, but badly violates condition 1. So how can we satisfy condition 1? So, all right, so we'll define the R omega operator. So I'll do this for a general x. So R omega of x, AB, will be x is a matrix. So it'll be n squared over m times xab if AB is sampled and 0 otherwise. And the idea is that R omega of x is equal to x in expectation on average. And we'll hope that R omega of x is not too far from x in subsets.
You mean on average when you are taking the randomization over omega?
Yeah, if we take the expectation over the samples that we pick, then yes, okay, so our starting point again. Our starting point was M. So now, if we want to satisfy condition 1, so note that applying R omega, so for any x, R omega of x will satisfy condition 1. That will likely break, but it'll break condition 2. So what will happen is, so our first attempt will be R omega of m. So the error that we'll have to correct for is, so we want P transpose of this to be, so we would like that P transpose of this is equal to m. Our error is the difference that we have to correct for is the difference between them. Well, we can try and do this. We can try and do the same thing with the error, and get R omega of m minus R omega et R omega m minus m.
So this is the second guess for T.
Yeah. Yeah, all of this is for T. So this will give a new error term. But the picture in a sense that we're alternating between r omega and pt. So the idea is that as we keep on alternating, we get like our error gets smaller and smaller, and then like there's one final step where we have to say, and then like there's one final step where we'd have to just take care of the error term and satisfy both of these at once.
So there's a limiting argument showing that this exists by some limit argument. The fact that there is a t like that follows from what you just said, and if you go all the way
So,
to the limit.
Okay, so one thing I should note, actually, so a few things I should note. You don't want to apply this too many times, because it turns out in order for this argument to work well, you'd like yeah, and each iteration I'm taking independent samples. So like yeah, taking a fresh set of samples each time. So every iteration of this. So I multiply the final bound by the number of iterations that I do, and actually this is why rect gives a log n squared. I get log n squared rather than log n. Like it is possible that if you do a careful argument, that could be removed, but I'm not sure.
So it's possible that if you take a random omega and you just take the limit of this, then it gives you.
So here I'm not quite taking a limit.
I understand you're not. Yeah, so then you're left with some finite error you have to fix.
Yes, I'm left with some finite error, but for that, let me say that so let's say that we're ignoring the third condition completely and just want to satisfy the first two. The thing to note there is that with high probability, and let's say like instead of UV transpose, we have an X here. So the thing to note is that that this here gives a system of linear equations. And the number of equations is like 2 times n times r. So the idea is that, but the number of variables is the number of entries that we sample, which is considerably higher. So the idea is that you have more than enough entries that you can find a solution to 1 and 2 simultaneously. The trouble is if you do that from the beginning, you have no control over its norm.
The first two things together are you can actually show that it's a well conditioned linear system. But I mean in the sense that all the eigenvalues of the linear system are nice, but this would only allow you to control the Frobenius norm of T. But you wanted to control the spectral norm, and I think that's why.
So after many iterations, that will be small enough that you can bound the spectral
Yes,
norm
you
by
could.
the Frobenius norm.
Yes, after many iterations, your error is small enough that you can take one final step and satisfy them both at once.
So how will the correction look like? So you zero out some things and then you zero out more things?
I wrote down the final answer for what you get. One second, let me just find. Here it is. Okay.
No, but the zeroing happens only at the end when you solve the linear system. In the beginning, you're just going through these iterations with very different
So you don't, so you
Well,
are
the
zero omega
so
during the iteration, or you are?
But then when you project, it could go back to
Yes.
Yeah, yeah.
So yeah, one way to visualize it, that you have these two linear constraints, 1 and 2, and you sort of go to, satisfy the second condition, then you go to the closest point, second condition, to iterate you do orthogonal projections between the two.
Yeah, you will still need to take another omega. You started with some omega, and then you take another
The
omega.
final omega will be the superset of all. So it's something you just you build out more.
Okay.
okay, so yeah, I guess I'll end by saying like what this what this expression actually looks like. So here it's what the iterative approximation actually looks like. So let's define r omega bar to be r omega minus 1. So yeah, r omega has expectation 1. So this basically like makes this have expectation 0. And then the kth attempt is we'll take tk to be the sum from j equals 0 to k minus 1 of r omega j plus 1 minus pt r omega j minus pt r omega 1 times m. And I claim that all of these are bars. But the thing to note is that this attempt does satisfy condition 1 because everything has some r omega in front of it. I should say that at the end we'll take the final samples to be the union over all the samples we've taken. So it turns out that so it's not too hard to show that if you take the error of this attempt is this here. And the idea is that applying PT after applying an R bar omega makes the matrix smaller. Yeah, in norm.
It's just a concentration bound.
It's a concentration bound. So this is why the error gets smaller and smaller, and then so one part is to take a final step to satisfy conditions 1 and 2 simultaneously, and the other part is to show that the norm so the other part is to show that the norm of the norm of what you get is at most 1. Yeah, and I think I am I'm out of time, so if you want to hear details about that, you'll have to ask me or David in person.